Is it not?
In the chat. Nope. I
don't know
checked.
what that's about. What? I wonder why that is. I might have to get in touch with her. Hope. And let me check. See what that looks like on the graphics as well. DP's new thing on. And yeah, we are live with nobody. Why is that graphic? Come on, get over it. Let's have a look. Hey, that looks fucking good, that. We are live. Look at that. Have you seen it? DP. Let me check that out. Nobody else is looking.
Yeah, I've seen it.
Looks fucking brilliant. Yes. Look at that. New graphic package. We are rocking. Just the same sort of thing as usual. But I mean, this is a... Said we might not do it, but we have had... Oh, who's that?
Yeah,
DP.
sorry, that was me. Yeah.
Let me get the Discord on. Right, so last night Blue Marble did a video. I said I'll go over it live for my Patreons. I didn't. I just said I'd go over it live. So I've never seen this video. I haven't got a clue what we're going over. We're just going to go over it. Sup, Jess? Let me get... So what this is us going over a video that Blue has gone over. Let me get the live screen on here. You guys are going to need the live screen. In like Pontchartrain and main screen there. Let's see that transition. Oh, look at that, right on it. So we are going to go over a Blue Marble video. Oh, wait a minute, before I go over this, let's give all of the, it's Flat Earth, obviously a Flat Earth channel. It's got the Flat Earth tag on it. Lake Pontchartrain Causeway, proof of Earth curve. Blue Marble Science. The catch is several years ago, Jesse Kozlowski and Soundly mapped the Lake Pontchartrain Causeway and showed conclusive proof of Earth curvature. Of course, globe denialists ignored it, so I thought it might be a good idea to revisit it. So that's what he's doing. Somebody's told me to watch this. I'll not give it a like, and we don't need to see his intro. Oh, look. Oh. Hey, steady on. Look, there's me. Using my graphics. And he's, should we actually do that? And get something up there. What have we got? I'm going to have to put a We Are Live.
Maybe just cover it with the King of the Bluelings.
Oh, I forgot that. I don't know whether I've got that on this one. I'll have to put a We Are Live over here. We don't want to... There we go. There you go. We don't want to be getting him in trouble. It appears Blue Marble Science might have copyrighted it, so we don't want him to do us for copyright. Oh, let's put it over there. There you go. Just hide it off. Right, now. I'll pause it whenever, but if any of you guys pause it or want me to pause it, do your best impression of Blue, and I'll pause it for you, right? It'll be interesting.
Well, hello everybody. Welcome to Blue Marble Science.
Hey, Blue.
This video is going to be about the Lake Pontchartrain Causeway and measurements that prove the Earth is a sphere.
Oh.
Well, proves it to everybody except a guy like this guy.
Level is horizontal. Yeah? Oh, that's nice.
No.
Warning. Severe facial and monitor damage alert is in effect. Get out those oven mitts. Push the monitors back out of punching range. And let's light this dumpster fire and have some fun. So let's get into it. This is Lake Pontchartrain, as seen from Google Earth.
What an opener. Gonna have to
Now,
start
for
doing
those
that.
of you who aren't familiar with Lake Pontchartrain, it's a rather large lake, and it's situated just north of the city of New Orleans, Louisiana. Lake Pontchartrain is unique in one respect, and that is it has a causeway crossing it. That causeway is 24 miles, or about 38.6 kilometers in length. That makes it the longest bridge in the world over water continuously. But it's absolutely straight, and that...
Is that right? Really?
Wow.
That's a...
Yeah, I think other bridges do island hopping. Like that one in China that's, was it 127 miles long or something? It's it hops between islands.
Okay. So there's no longer bridge than that. That this is the longest bridge over water. Is it? That's
might be worth checking, doing a bit of fact checking there.
Yeah, I like it. I like it. I've learned something. Thank you very much, Blue. I'll check it though, just to make sure. I don't want to be looking silly saying it to other people.
But
it just might be China.
Is on the planet.
Well, yeah. Wait, we see.
To be able to actually see the curvature of the Earth.
Oh, wait a minute. I might have missed a bit.
Longest bridge in the world over water continuously. But it's
I can already tell you that's false.
And that makes it one of the best places on the planet to be able to actually see the curvature of the Earth.
Right? It's one of the best places on the planet, apparently, to be able to see the curvature. It's fucking brilliant we've got Rakia there. That's why he's never done that.
Remember C, he said.
Yeah, I like that. You say you... Should we get into the bridge thing? We'll just put a little note in there that Emma says no. And we'll come back to that some other point. Okay, we go.
Here's a picture of the causeway. That's taken from about the 15th story of a hotel on the south shore of the lake.
That's it.
You'll notice a couple of large marine spans where the elevation of the causeway rises up considerably to allow boat traffic underneath. They look extreme in this photograph because you're looking down the length of the causeway with a very long telephoto lens. And what happens is a visual effect that's called foreshortening. If you're up on top of that causeway, at the top of one of those marine spans, the view looks like this. So it's not nearly as extreme as that photograph shows. That view would be from a point about where the arrow is.
Right. Can I point out that in this picture here, the horizon is there all the time, all the way across.
Yep.
And the bridge is here. They weren't hoping that the bridge should go over the horizon, were they? Because the horizon's higher as it is over here. I'm unsure. I'm not sold. It's interesting, that, though.
But flat earthers take a look at this and they'll immediately begin with denial. They'll tell you it's refraction or
Denial
it's
of what?
perspective. They'll tell you it's being caused by some...
What denial? I mean, I know the flat earthers, and Blue doesn't like flat earthers, but what's the denial? That it's a picture took by Soundly.
Unknown optical effect nobody's ever heard of. Frankly, anybody that could see a moose in the road at a distance of 50 feet doesn't have any trouble seeing the curvature in that causeway. But for some reason, flat earthers do, and I think I know why. So now, let me introduce you to the two guys that originally did this work. That's Soundly on the left, and that's Jesse Kozlowski on the right. Soundly is a YouTuber, and he's probably made more video and photographs of the Pontchartrain Causeway than anybody on the planet. Jesse...
Do you reckon? I mean, I wasn't around when Soundly was here doing his 3 years study of Lake Pontchartrain. But do you reckon he's done more videos and stuff?
Bit of a difficult claim to substantiate, isn't it?
Well, yeah. Since Soundly's not around anymore. I've only ever seen that picture of... I've not really seen any much more of his other work. Have anyone else seen his substantial...
No. As far as I know, he went there once and took a photo and...
Yeah.
And that was it.
Bam!
Yeah, and bam! That's Jesse does that. I hope he goes does that.
Professional land surveyor. Several years ago, Jesse took his GPS equipment down to New Orleans.
Did he say?
Than anybody on the planet. Jesse, meanwhile, is a professional land surveyor.
Only a land surveyor? Oh. I've got a land surveying certificate. And Jesse's only a land surveyor. But I bet he'd be upset hearing that.
Several years ago, Jesse took his GPS equipment down to New Orleans. He mounted it in his car, mounted the GPS receiver antenna on top of the car, and then drove across the causeway taking position measurements about every 10 meters. This is the GPS antenna mounted on the top of Jesse's vehicle.
Pics.
It's about 1.5 meters above the road surface. And there is the GPS receiver. You can see there's the height of the antenna, 1.53 meters. The distance of 10 meters is what he has selected to take his waypoints. And you see the accuracy down here. The horizontal accuracy at the moment I took this screenshot was 9 millimeters, and the vertical accuracy was 15 millimeters. That's amazingly precise compared to the accuracy we get with GPS in our telephones. But that's because Jesse is receiving constant corrections from a base station at Louisiana State University. While he was doing that, Soundly was up in the 15th floor of the Marriott Hotel there on the South Shore, videoing.
A base station? He's getting updates at a base station somewhere, Louisiana University. Would that be where the ground-based satellite would be, the main hub? I don't know.
Going the causeway while Jesse was doing the measurements. Now, before we get into the actual measurements, let's take a minute and talk about GPS, because that's what Jesse was using. Not the kind of GPS you and I have in our telephones, the kind of GPS that professional surveyors use.
Oh.
GPS is an amazing system. Our GPS receivers look for signals from the satellites And when the receiver can see at least 4 of those satellites, by knowing the position of the satellite itself and by measuring the length of time it takes the radio signal to travel from the satellite to the receiver can determine exactly how far it is away from each of the satellites. Now, knowing that through
that sounds fantastic. I'm not too sure that's right. How can the base station know how far away it is and know the positions of where the supposed satellites are meant to be, and then tell how long the signal takes to get to it? I'd have to be explained that. That sounds a bit... Can't process that in my head.
process known
Never
as
have been able
trilateration.
to.
The GPS receiver can then pinpoint its location. Sounds simple, but there's a lot more to it than that. We won't go into all of those details. That's not terribly important to us for this discussion. What we want to understand is how we can use the GPS position data to reveal the shape.
And just thinking about it as well. So the GPS receiver has to know the exact position of the satellite. And I'm guessing, seeing as it's saying to the 15 mil, that it must know how far away the satellite is, exact position when it sends the thing to that 15 mil, right? And then it's got to be able to time the signal, however it does that, from when it sets off to when it gets to it, and be exact.
That thing he showed said it was RTK. You have to have a base station set somewhere.
He did say Louisiana University, yeah.
No. From what I've read about that RTK, like that thing he had on his car, gets a signal from a state. Like it's like a 2-piece deal. From what I understand, you can't. It's not like you just have a device.
Yeah, he said that he got it boosted from Louisiana State University, the base station.
What Buster's saying is you have to have one set up on your site. That is, but I'm not sure about that. I think you can log in. Like the Louisiana State University is 60 miles away from where he's at.
Yeah, well, I mean that's what Blue said.
But there's a maximum limit.
Well, I would be the first person to say I haven't got a clue about how this. I mean, it sounds fantastical that base thing that he's got in his hand there knows the exact position of all of those satellites and the position of them when they were sending the signal as well, and the time that they sent the signal, because it only receives the signal. That's all that base thing does. So I mean, it sounds magical to me, but I mean, Blue's obviously the one to work that out.
Saying, the thing he had on his car, I was, from what I've seen, the thing that Blue showed said RTK at the bottom.
Yeah.
And from what I've seen about it, it's a 2-piece deal. You have to have like this base station you set up, then you have your movable other bit that I guess what he had on his car.
Yeah.
I've never seen where the RTK stuff you have like just a standalone one piece of equipment. But I could be wrong.
Yeah. I mean, like, you plug it into your car, obviously. I mean, have you ever seen the car ones?
Yeah. It comes with an adapter.
Yeah. State-of-the-art surveying equipment that you put on the roof of your car. Drive over bridges. Every 10 meters, it knew where exactly all of those satellites were. It sounds like magic, to be honest, but I mean, it's just me. I'm used to the usual surveying. just plain old horizontals and measuring vertical heights.
Shape of the
Carry on.
causeway over Lake Pontchartrain. Now, GPS or GNSS use a coordinate system that's referred to as Earth-centered, Earth-fixed, ECEF coordinates. There's an x-axis, a y-axis, and a z-axis. The x-axis is centered on the zero meridian, or the prime meridian. The y-axis is perpendicular to the x-axis. You can imagine those two axes lying along a plane that would be formed by the equator of the Earth. The z-axis passes directly through the International Reference Pole. That's essentially the geographic North and South Pole. So the origin for this coordinate system is at the center of mass of the Earth. Now, our GPS...
Okay, so...
You hear that?
Yeah. Well,
That was the most ridiculous statement I've ever heard.
Z is at the north, right? So in the center, you've got the north. And then you've got a plane of reference, the X and Y, right? Sounds very familiar. Sounds like a Cartesian coordinate system, doesn't it?
It'll even look that way, yeah.
Yeah.
But
Look,
your Z never moves. Like, it's just one. That's it.
yeah. Yeah, that's exactly how I would imagine a horizontal plane and a vertical.
Would you imagine the center of the mass, though?
Well, what's mass? I mean, nobody's defined mass, but that's what I'm just looking at it as though, like, there's even a little bird up here. Look, it's falling over. It's got a broke wing. And there's an arrow pointing at it. But
if your Z is only one from pole to pole,
yeah,
how do you use a coordinate system when it's just that? There's so many problems.
Well, no, I don't see there's anything wrong with that, to me. I don't see anything wrong with that at all yet. That's exactly how I'd imagine.
But if you're moving along your X or Y axis...
Mm-hmm. Like you would. And then you
how
go
would
up
the
and
Z
you
work?
use the Z. It's that, like, this is your elevation plane.
Yeah, but he's saying the Z is just that one position north
all
and south
parallels. Yeah, I know they're all parallel, aren't they? All of these planes and all of the Z, like a vertical datum. The Z's on a vertical datum, and you just go out from
parallel.
there.
Yeah,
Obviously,
right on.
just put a center in the middle.
This receiver determines the displacement on the x-axis, displacement on the y-axis, and the displacement on the z-axis, and that gives us an x-y-z coordinate for our position.
Yeah.
We can see the same thing in this graphic.
Wait, it gets better.
Whoa, hey, what?
Y displacement.
What's going on here?
This is it.
It's put a nice thing. Here's your X and your Y and your Z, and
That Z that you thought, you're wrong.
Oh.
Yeah.
Egocentric. I see.
The Z moves to
egocentric Z. Yeah. Understandable. Yep. Okay, with him.
Z displacement. We can then easily determine the resultant vector. Now that's going to give us our exact distance from the origin of the Earth-centered Earth.
There's now better than putting a bit of Greek lettering in the center, right? Once you go to nobody's ever measured any of these angles here. This is obviously fictional, unless this is some sort of a dome he's got here, and these are just elevation angles. I don't know.
Fixed coordinate system. But it also might be the origin for a totally different coordinate system.
Might be.
Maybe it's a state plane system.
Oh.
Or maybe what we want is latitude and longitude, like our telephone tells us. Well, that's fairly easy. Angle phi is latitude, angle lambda is longitude. But there's a problem that flat earthers have here.
Wow.
And it's with this z-axis. This is the z-axis of the Earth-centered, Earth-fixed coordinate system. And they get that confused with this up-axis.
The other z-axis.
Now that up-axis...
Yeah, I told you.
Yeah. Don't confuse your z-axis with your z-axis. I mean, that'd be crazy, wouldn't it?
Yeah.
I like it.
Our elevation above mean sea level.
Zed.
Listen to this exchange.
If let's say that we got our GPS system and we put it in the XY coordinates and drove over the bridge and got a 5-point-something meters all the way across. Yeah, this is me. It's not me now. This is me. Where's the curve come from?
See what I mean? Absolutely clueless.
What?
You measure your coordinates, your XYZ coordinates, not only your elevation.
But Z is the elevation, right?
No, it's just the position.
Yeah, it is.
It's not. It's just. Yeah, it's just your position. It's not related to elevation.
It is. The Z is the elevation. That's the vertical datum. It is.
It's just your position along the vertical axis.
Yeah, the vertical datum. Yes, exactly.
So you see the problem.
What fucking
we
problem?
see the problem, Blue.
Yeah, the problem. You're going to say that Z there isn't the same as this Z over here when it is. This Z here is your imagination of this Z here. This, I'd say, is this in your imagination. You've got a law of identity problem because the Z's going to turn into Z. But hey, it's okay. When I was thinking Jesse was surveying over the bridge, I was imagining the Z as the state plane coordinate system. If Jesse wasn't actually using that and he was using a different Z axis, then I'd like to see it. Hopefully Blue's going to show us that and not just slap his forehead.
If you have a limited background in mathematics and geometry like this fellow, it won't be necessarily immediately obvious to you that GPS elevation data you're looking at has already considered the height of the ellipsoid and the geoid.
What?
You're effectively seeing your elevation above mean sea level. And that elevation data that looks like a z-axis to you is not the z-axis of the Earth-centered, Earth-fixed coordinate system that GPS is based on. So now let's have a look at how we could use the raw GPS XYZ data to reveal the shape.
Is he just sort of gone? The Z that you're thinking of isn't the Z that I'm thinking of.
That's what I was asking a minute ago.
Yeah.
What happened to we're always on top of the ball? Lou?
Yeah. Well, yeah. Why is Z up there and not Z up there? I think you'll find that this is the Z that I was definitely talking about, right? And you think it's this Z over here. Z at an angle Jesse was using. Nice. I mean, like, I wasn't aware of that.
We got a fixed Z.
Yeah. The GPS coordinate system has a tilted Z on it when going over the bridge. Be handy to know that.
Shape of the causeway.
Mm-hmm.
This is just the coordinate system. We have an x-axis, a y-axis, and a z-axis. Let's put some points in space. We'll put a point there, and a point there,
oh, nice graphics,
and a point about midway between them. Now let's draw a line. If the Earth were flat, those 3 points would lie in a straight line. Now we can take that XYZ data and we can calculate the length of the vector to each end of the causeway, and we can get a distance from the origin to the center of the causeway. Now let's toss the Earth back in here. Those 2 outside points are the starting point and ending point of the causeway. That line would be a chord line. The red line is the causeway itself. If the causeway is following the curvature of the Earth, that center point is going to be up here. And we'll be able to see that in the length of that vector.
That was a bit... I might have to go back over there. Could have sworn he said calculate.
Just to reiterate, that thing you showed at the beginning with the numbers on it?
Yeah.
The data on the bottom. It would be nice to know what he used. Does he ever say, like Jesse?
What?
The kit that he used.
The unit, I think maybe. I think Blues had a word with him, so.
I think he shows some of it later on in the video.
Well, on that thing he showed it on the bottom, it said the RTK, and everything I've ever seen, you have to have a base station and then the bit you move around.
You ready for this geometry?
Oh yeah.
Right, he's got a coordinate system with 0, 0, 0 at the middle, right? Never been measured. I haven't got a clue. I don't know who's telling him he's 0. I think maybe it might be the satellites that he's imagining are a 0, 0, 0. But he said at the beginning of the other video that he did it across the lake. I'll go over that again at some point. I might have to put all of these bits together. Right, but let's listen to this.
Let's put some points in space. We'll put a point there, and a point there, and a point about midway between them. Now let's draw a line. If the Earth were flat, those 3 points would lie in a straight line. Now we can take that XYZ data and we can calculate the length of the vector to each.
He can just put randomly 3 points in space and you can calculate the XYZ data from that. Like, how do you just randomly put some points in space and then calculate something from that? I don't understand. How do you use Cartesian coordinates, put 3 points in space, and then say, if we're on a flat Earth, like, what? If we're on a flat Earth, then this line would be straight. What would be straight? The line? The 3 points that you've just put in space? Is this one of the things Blues put in his thing to confuse us?
Each end of the causeway, and we can get a distance from the origin to the center of the causeway. Now let's toss the Earth back in here. Those 2 outside points are the starting point and ending point of the causeway.
How do you just take the Earth out and then pop it back in again? Where does all of this come from? It's inside all of it.
That line would be a chord line. The red line is the causeway itself. If the causeway is following the curvature of the Earth, that center point is going to be up here. And we'll be able to see that in the length of that vector, the distance from the center of the Earth to the center of the bridge. Now let's have a look on a flat Earth. We've got
the center of the Earth.
I would agree. That
is delusion. Yeah. Sheer delusion.
Total
right.
Imagination.
See, what he's done is, like, on his model, all of these distances are the same, aren't they? So where the fuck did he get this line from? Why did he need to calculate this? Because this is one point at the end of the fucking bridge. And this is another point at the end of the bridge. He's meant to have drove over the bridge.
Gets a lot better.
Whoa, I'm struggling.
Don't get
here.
mad now, because you ain't seen nothing yet.
The distance from the center of the Earth to the center of the bridge. Now let's have a look on a flat Earth.
Oh,
we've got the causeway north end on the left.
What?
I told you. Zoom up.
Right.
This is a flat Earth to Blue, is it?
The green line is mean sea level, in other words, lake level, basically. The red line is the causeway itself, and the GPS elevation is simply the difference between mean sea level and the road surface.
Right, now, Spot On's been big on this for doing canals and sort of. We've all been on that. Does that look like a normal elevation profile to anybody, right, of water? Of a canal? Of a lake?
Yeah, basically, yeah.
I know he's saying it's flat Earth, but I'd say that's just a normal elevation profile of water that I've never seen any other. Well, I have, but it was Blue that drew it. I hope he's going to do it again. But that, if the Earth is flat, looks like every elevation profile I've ever seen. So maybe all of those should come with a little qualifier. If the Earth's flat. Worth trying.
This is flat Earth data.
Yeah, this is flat Earth. Watch what you're doing.
We can use the XYZ coordinate data to determine a distance from the origin to the north end of the causeway and a distance from the origin to the south end of the causeway. And we do the same thing for the center. But what if the Earth is spherical?
Look what you did there,
the north
Blue.
end of the causeway and the south end.
He's done it again.
I told you. Gets
Has
better.
anyone ever seen an elevation profile like this? Because this is if the Earth is spherical. I've never seen anybody else ever draw an elevation profile like this. So, I mean, judging by that, I mean, it might just be Blue. Might just be only Blue. But, I mean, hey, here we go.
Of it. This time, we're showing the geoid. The causeway is still being represented by that red
Big
line.
fucking Wazin hump.
And our GPS elevation is simply the height above the geoid. It's still essentially elevation above mean sea level. So now the green line is the chord line.
Chord line.
And we can get a distance from the origin to the north end of the
Blue,
causeway.
It's actually not a chord
to the
line.
south end of the causeway. And on a flat...
You not think it's a chord line?
No.
Just right the hump.
No, it goes through. He's right.
It goes through.
Yeah.
Secant.
Yeah. Yeah, it's a secant that. Well done, Buster. Buster spotted it. Maybe that's one of your little mistakes you've left in there, Blue. Well done. That was one for Buster. Anybody else spot that? It's not actually a chord, is it? Because it goes beyond the circumference. It cuts the circumference and goes beyond it. It doesn't stop. A chord stops at the circumference of the circle. That line goes past it. So that's what we call a secant. It's just a technical geometry term. But Blue said he'd be leaving a few of these for us to spot. Shout out if you see any others. Thank you, Blue. We're liking this.
Buster and his chords.
Yeah.
What can you say?
Yeah. Buster knows a chord or two.
Oh, yeah.
He knows a not chord when he sees it.
At Earth, that point would be in line with the north end and the south end. and our distance from the origin would look like that.
Right in the middle.
But if the Earth has curvature and the causeway has curvature, the point we measure in the center of the causeway will be up there. And
wow, so he's right. Like, this is the shortest distance between these 2 points. And he's saying if it's spherical, it's not going to be here on this line. Like everybody else has ever drawn them. Oh, hump. So take note.
We've got a hump.
If the Earth, he says, does put it, if the Earth is spherical, it doesn't lie on this straight line here. It's up there.
now we will have a distance above that chord line, which we call the sagitta. This is how we can reveal the shape of the causeway. Now, this is a sample of the GPS data that was collected by Jesse.
And
this is out of the work that Walter Bislin did. I've just taken one small section of data so you can see what it looks like. There's a link to Walter's website right there, and I'll put it in the description too. You can look at the full data set, which contains more than 6,000 points. The point we're looking at here is point number 1660. It's on the northbound lane of the causeway. You'll also see GPS elevation data provided. You might wonder why that's even there. Well, there's a very good reason for that.
So they know what elevation
that causeway
is.
has a number of those marine spans. You want to be sure that you're analyzing data that's on the level part of the causeway, not on one of those marine spans. I analyzed 3 points on each side of the causeway, one at the north end, one near the south end, and one somewhere near the middle. I'll just show you where those points were. That's the south end. You see those 2 points. There's the midpoints. And there is the north end. So let's have a look at this. If the Earth is a flat plane, the three vectors V1, V2, and V3 should form a straight line. On the other hand, if the Earth is spherical, the vectors are going to describe an arc.
Sorry,
yeah, this is what he did earlier too, right? If the Earth is flat, he says, which is ridiculous in itself. But that BC line there, right?
Yeah.
Has a distance. And if you conflate it to that red line on top, the arc there, that distance can be longer, yeah?
Well, no, on his model, like V1, V3 are like, this is so stolen concept, but it's like a reverse stolen concept, isn't it?
Yeah, because like the earlier picture, when he goes and he puts these V1 and V2 on that earlier picture when he says if the Earth is flat. Well, if the Earth is flat, it has no radius, right? Blue?
Yeah,
so
this isn't
where
here.
does these
What's
vectors
this whole
come
ball
from?
isn't coming here.
Yeah.
Like,
they don't exist, right, Blue? These vectors, you just made them up.
Yeah. Yeah, like this is the line that you put on there at the beginning, and they all said 5.8 meters all the way across. You just Imagihumping. Like this blue marble here is causing you to Imagihump. It's got to come from the radius, right? Because you've got to see what's going on here. If this straight line is put on a circle, then it can't be a straight line, I think is the argument. But I mean, if this is the best we've got.
Yeah, you can take that straight line distance, BC, and say that's the distance along the bridge. And then just make the sphere fit perfectly to where it is in the picture now, right? And since you have a presupposed radius, you can find the ratio between, or from the chord line to the arc, and from the chord line back down to the center of the sphere that you already presupposed to begin with.
Well, it's the total assumption that those vectors are converging.
Mm-hmm. Yeah. How'd you get that?
Yeah, I mean, there's no proof for that. He's just showing it, baseless claim.
Mm-hmm.
Yeah, and like, could we safely say that at this end of the bridge to this end of the bridge, there is a shortest distance from A to B measured? And would we be able to assume that's a straight line? Or would somebody else assume that there's a whazzing great big fucking hump in the middle? I'm not too sure. Like, I'd say that's a horizontal distance, the shortest distance from one end of the bridge to the other.
Yeah, and it's definitely shorter than the red arc going
Yeah.
across.
That's longer.
Yeah.
You'd say Jesse drove a longer distance than the shortest distance on the bridge. I don't know. I mean, he's got a few numbers there. I mean, but this is...
Maybe this is the mistake you wanted to left in.
Yeah.
Record it.
Maybe. I mean, like, we are just dealing with basic concepts here. You directing this video at me saying I don't understand it, Blue, if you're going to watch this. I mean, I wouldn't bother. But, I mean, I don't understand where the humps come from. You've just drawn it on a circle, but, like, the shortest distance across the... I've never seen anybody else draw a humped elevation profile ever. And you've done it here again. I don't know.
With a radius r. Now we have the XYZ data that was collected by Jesse, and calculating the distance from the origin to the data points is very straightforward. It's simply the square root of x squared plus y squared plus z squared. You see those distances displayed there. Now let's put this on an AutoCAD drawing and see what we end up with.
Wow.
This is for the southbound lane, and the north end of the southbound lane is there on the left side. The origin is down here at the bottom where the red arrow is. The causeway itself is way up here at the top. In fact, at this scale, you can't even see it. Notice the dotted green line. That is the AutoCAD vector that I've drawn, and that is telling you that that's the vector I've selected to measure the length. Notice that the length is 6,372,796.257 meters.
What?
That matches our calculated distance.
What?
6 million?
6 million?
6 million meters. Did he say that?
Yeah. 0.2570. 4 decimal places. That's when he was saying earlier about he knew where the satellite was, right? Exactly, his GPS system. Like I say, I don't know how these GPS systems work, but they would have to know the exact position of these things, especially for doing a vertical height datum, right? In order to get your... I think that's why he had to measure it on the roof of his car. So it had to know the distance... No, wait a minute. It was the distance of the center. So it knew the GPS system, right? Follow it with me if you can. The GPS system must have known exactly how far the satellite was away from the center and where the GPS was in the middle. No, it must have told him where he was in relation to the center when he got the signal received from the satellite. Would that make sense? Some complications there, isn't there?
I see what you mean. Yeah, you could compare the radius to the distance from.
How would you know where you are in order to work out where it is in relation to the center in order to make your triangle for where you are. Because that's what you're after, where your height and your position, not where the satellite is and how far the satellite is away from. Right?
Yeah, you wouldn't be. You wouldn't be able to do that.
No.
Not based on that anyway, yeah.
We'll have to go over that, and because this is another thing I've been asking people for God knows how long. How do these satellites actually work?
I think that's
in
not
their
what he's
imagination.
doing, though. Sorry.
Go on.
The thing you showed early on in the video, if his thing was RTK, I think they're barking up the wrong tree with what they're saying is GPS.
With these numbers. Yeah.
Well, early on, Blue showed where, it was a data page, and at the bottom it said RTK, and that's something that should be looked into.
Yeah, well, I mean, we can go into that, can't we? I'd love to get into this GPS and how it all works and all of that, because I bet it's fascinating looking into it, right?
Well, it's just that, like, when they keep saying GPS and satellites, if that's what he used, I don't think it has to do with that, but I could be wrong. But everything I looked into, because I heard somebody else mention RTK a whole lot ages ago.
Yeah, I'm looking at all of these other things.
I think they're misrepresenting what the RTK is, because from everything I looked at, it's just a rover unit that gets sends and receives a signal from a base station that you place over a known marker, and the accuracy of it depends on how accurate you set it up over a known benchmark. The base station, anyway.
I'm just looking here as well, and he's got an angle underneath, and this one's 90.1731. This one's 270, and this one here is 89.821. Slightly different, maybe on the axis, but I've always thought they were all perpendicular to each other. So, how this one isn't 90 and this one isn't 90 yet? Not too sure, but. Maybe another one of Blue's mistakes. Maybe not. I mean, who knows? Who knows where Blue could have put a mistake in here that we don't know about? 2 scale as well.
We do the same thing at the center and the same thing at the south end. Now let's zoom in at the top and see what that really looks like. The green line is the chord line.
Look, it's me again. He loves putting me on there, doesn't he?
Wait, he changed the angles, you said? 270, 290s?
Here. This one's 90.1731. And this one over here is 89.82. And this one's 270. So.
Well then, okay.
Yeah.
That's cool.
Because I'm guessing this one's in the middle. And, I mean, well, I don't know. I mean, who knows? All of this computer stuff, I mean, we'll have to get Rakir on it. He'll know.
The green line is the chord line.
The chord line.
That would be the straight line between the north end and the south end of the causeway.
That would be the shortest distance between one end of the bridge and the other end of the bridge. The very shortest distance between the two.
The causeway is that white line. That's an arc.
Not going
the green dot
distance.
Was the GPS XYZ position measured at about the center point of the causeway. And the sagitta is 28.1177 meters. I asked AutoCAD to tell me what the radius of that arc is, and it says 6,342,337 meters. Well, the actual value should be 6,372,817 meters.
Whoa, no
so
way.
that's about 0.5% less. But let me tell you what that actually means. If that GPS position
plugged your numbers in,
is
right?
inaccurate by 1/10 of 1 meter, we would end up right on top of the accepted value for the radius. Let's have a look at what the northbound lane looks like. Again, the green line is the chord line and the white line is the arc.
Done them individually.
And on the northbound lane, based on the points I selected, we have a sagittal of 27.53 meters. Now that's not unexpected because the distance I used between the points on the northbound lane were closer together than the southbound lane. You would expect the sagittal to be less. The length of the arc is less. The radius in this case is very similar to what we saw on the southbound side, actually a little closer, but still about 0.5% off. And this was the data that Jesse presented. His sagittal was 28.457 meters.
So this is the first time I ever saw anybody draw an Imagihump. Jesse Kozlowski, 28.457 meters. I still don't believe it's there.
But he used a distance, an arc length, even longer than my southbound arc length. That's the end of that. That causeway is not flat. And you flat earthers need to stop talking about a hump of water.
What is he talking about?
There's no hump of water. That causeway is following the curvature of the
There's
earth.
no hump of water.
Just like the water underneath it is following the curvature of the earth.
There's no hump.
But there's something else that's pretty interesting. Now we know that the earth is an oblate spheroid. We know that it gets a little bit chubbier as we go toward the equator.
Chubbier.
That means that
Chubbier.
Did I miss something, or did he say like with those points that he did on the north and southbound that the values were off by 0.5%?
Yeah, I think so.
What's a 0.5% error of 6 million?
Not got a clue.
Well, would you say it'd be more than 28 meters?
Literally, I wouldn't like. I just know there's no 28-meter hump of water.
No, I'm just saying within what he showed, he said there was a 0.5% error of 6 million. Oh, 6.
I don't even know where he got the 6 million meters from in the first place. That's meant to have come from his satellites. But his satellites aren't fucking measuring his position if they're measuring the center of something that they've never measured in the first place.
But what I'm getting at is, if there's a 0.5% error, is that what he was saying?
No, I think he was saying when he did it and he calculated it, he was within 0.5% of the real number, right? Like Jesse's gone over there and measured it with his GPS system, and he's got within 0.5%. So, I mean, that's near enough, isn't it?
Not really, not if you're 0.5%.
He just drove over the bridge. You can't have too much, It's not as if it was a serious surveying project, is it? I mean, obviously not. I've never heard of roof car surveying driving over bridges before. I mean, I know Jesse works for a professional outfit, so obviously that might be one of the things that they do nowadays. I've never heard of it.
Maybe they were beta testing new tech, so surveyors won't have to get out of their car.
Yeah. For the surveyor on the move.
Yeah. No longer do you have to get out of your car and do anything. You just get yourself a four-wheel drive and drive.
Yeah, just drive around the place. Well, what are you doing? I'm just surveying. Cool. I can survey on the way to the shops.
That's 30,000 meters.
Yeah, constant. Yeah, earn a bit of pocket money. pretty costly though for an initial outlay for your rooftop aerial unit.
What about you could create a website, know your elevation?
Yeah.
Just my thing with blue, and if you're getting a 0.5% error on the 2 points, how would you ever say that you've got a sagittal of 28 meters when the error is, would you say, 30,000 meters?
No. That's how close he was to the real one that they've never measured.
Oh, the other supposed.
Yeah.
Yeah. I get it.
Yeah. Equipotential angle of adjustment to the center.
So is the said the accepted radius value, is that the real one, or is what Jesse did the actual?
Don't know. I think they must compile them, all the rooftop car units.
Yeah.
Constantly doing it, and then they can just sort of average them, can't they?
I guess so. Within a 0.5%, maybe.
Yeah. You get more accurate that way, I think. Like I say, I'm not really any good at this GPS stuff. Blue's obviously much better equipped at doing this than I am.
I wonder what the GPS would read if you just drove beside the canal.
Yeah, on a bike. Do you reckon we could put one on? I could get one on me hat.
Yeah.
And go on the bike down the canal.
Yeah.
Maybe we could integrate some of George's ideas and get like a piece of plywood and cut a hole in it and put.
Yeah, that would be good. Yeah, plumb bobs in the corners to keep it all.
Oh,
we could replace the plumb bobs with the GPS units on each corner of the plywood. Yeah.
Oh well, yeah. I mean, it's testing season, isn't it? All methods. Maybe the brawlers will be going out again. Maybe Jesse will be back. Right, gonna have to get through this. It looks like we're getting to we're on the slope down. Rumpus. This is Rumpus. This on the side.
Buster, if we're using that, get even more, more than 30,000 meters.
Yeah, we're getting to the big hump.
The causeway, that would be vector V1 for us. Should actually be a little bit longer than the north end.
Oh, it should be.
That's vector V2. And sure enough, we see that in the data. On the northbound side, I got a difference of 108 meters from the north to the south. And on the southbound lane, I got 109 meters. Again, the distance that I was measuring over.
109 meters where? What? Why is it only 109 meters? What's going on?
Is that to the center point?
I don't know. He's trying to say that because it gets a little bit chubbier around the centre, a bit pear-shaped. He stole it from Neil. Gets a bit chubbier. That one of them's a little bit longer than the other. And it shows it over here. Look, 108 and 109 meters.
Yeah, can't you imagine it? Come on.
I don't know where this 108 and 109. Where's that going to be measured from? What's that about?
From the center of the sphere. Come on, guys.
No, that's just meters.
That's 109 and 108. Like, one's longer than the other. So it's a little bit chubbier. But why it's 100 and something meters? I mean,
Yeah, that's not very long, that, compared to the bridge.
I'll just go back over that, because I don't know. Maybe this is one of Blue's mistakes that he's left in again. Pull it back to it.
We know
this is
it's
not a
little bit
mistake.
chubbier as we go toward the equator.
Chubbier.
That means that the south end of the causeway, that would be vector V1 for us, should actually be a little bit longer than the north end is. That's vector V2. And sure enough, we see that in the data. On the northbound side, I got a difference of 108 meters from the north to the south. And on the southbound lane, I got 109 meters. Again,
from the north to the south?
Yeah, I heard that. What's
From
that
the
mean?
north to the south. 108 metres and 109 metres from the north to the south. Is he saying going one way? It is northbound and southbound. It's a bit longer.
In the data, there's V1, 2, and 3, but on his blue ball, he's showing it's only V1 and V2. But he's saying the difference between V2 and V3 is 108 meters, I think.
No, V1 and V2. The V1
Difference
to
between-
V2 differential, it says there.
Yeah, but there's less digits in V1 on the first one on the northbound. It's hard to see. It's too small.
X, Y, and Z. V1 83727851. That's less. V1 minus V2. Well, V2 3726. Yeah, 687.
You have to put this stuff in the
That's the start and the end, isn't it?
This is the job tomorrow.
V3's in the middle.
With
Spot
Paul.
on. Somebody
Shit.
sort him out. So you've got, this is the start and this is the end. And the difference between the start and the end is 108 meters. 108 meters. The start and the end. The start and the end.
That's what I'm saying. Like
Goes up 1.5 meter, 108 meters. Is that what he's saying? And it's 109 meters, the difference between V1 and V2. If V1 is the distance from the centre, and V2 is the distance from the centre at the other end, then if the difference between those two is 108 meters, that's a 108 meter rise, isn't it?
That's what. Yeah.
Yeah.
Really?
Are
No,
you
he
guys-
can't be saying that, can he?
You have your imaginometry switch turned off, I see, right?
Yeah, but that's his. That's the length of these arms. That's the distance from the centre. That's his elevation.
Yeah.
And he's got a difference in elevation of one to the other. The vector length, the length of these arrows. Yeah. Well, does he not consider the length of these arrows being elevation? Because he's got 108 meters difference. Maybe that's got to be one of the mistakes he's left in there, right?
I would think so.
That's got to be right. Yeah.
If it's 108 meters difference, how do you get the 28 in the middle?
Yeah. Right. Well, I mean, the 28 in the middle could be to this line that they've just imagined there, but I mean, who knows? But I mean, that's definitely 108 meter difference from V1 to V2, and he does say meters. I'll just go over it again. Let's hear him say it again.
Should actually be a little bit longer than the north end is. That's vector V2, and sure enough, we see that in the data. On the northbound side, I got a difference of 108 meters from the north to the south, and on the southbound lane, I got 109 meters. Again, the distance that I was measuring over is slightly longer on the southbound lane. Well, is that...
Right.
I think he means 1 meter difference.
No, 108. Yeah, I know. There is nearly 1 meter difference between this one and this one. But he's definitely got 108 meters difference between this one and this one.
So he's saying from the north side to the south, it's 108 meters higher.
Of the vector. Yeah, the vector length is 108 meters difference. And he expects them for one to be slightly bigger than the other one. Which it is. It's a meter out, obviously. At least I think that's what he's saying. Like I say, I think that's one of his mistakes. But I mean, like, we may just not understand this at all.
Who would want to?
Yeah, I mean, like, I just like to do the usual, normal surveying techniques. I mean, it may take a while, but this just seems like it doesn't seem very accurate, to be honest with you, driving over the car and 100. So if you're going, are you going difference between 108 and 109 meters? So when you're actually going downhill or uphill, the change in the length of these things, but with no change, I'm guessing. I'm guessing those changing a difference here means that there's no change in the level, I'm guessing.
Yeah, but if you drive from north to the south, at the south you're 108 meters higher.
Well, longer on the vector, but I'm guessing they're going to just get rid of that and say, no, that's what level is. Level changes like this all the time, right? In order for you to imagine you're still on this surface here.
Well, so what is, if the length is longer on the southbound of the vector, what's that imply?
Well, I don't know. I mean, to them, it'll imply globe, right? I mean, how else could you have it if it wasn't a globe? I mean, that would just, if it wasn't a globe, that'd look fucking ridiculous, wouldn't it?
Not just globe, a spinning globe.
Yeah.
So SE, if the vector 1 is longer than vector 2, or the difference is 108, I mean, maybe 108 meters would get you your skateboard going downhill.
Oh yeah, definitely.
Always. I mean, that's 108 meters over 20 odd miles. I mean, that's definitely noticeable, right? Especially to have a 28.5 meter hump in the middle of that.
That's, yeah.
Surf's up. Yeah.
Fantastic. I mean, well done, Blue.
Fantastic.
This is great.
From the end of V2 then to the 108 meter up past V1, you'd form a right angle triangle. Well, not right angle in this case, yeah, but still form a pretty huge triangle.
Yeah. We're all aware in their spherical, fantasy spherical spinning ball that the distance from the north, their north pole, to the center of the Earth is shorter than from the equator due to this here, pear shape, due to the spinning. We're all aware of this, right?
That's what he's saying. Because of the pear-shapedness of of their model, he expects that this vector line at V1 to be longer than our V2.
Exactly.
Which he says it is by 108 meters.
Yep.
Right. So if they are governing everything from a 0 point, then that is a definite 108 meter difference. Just in the way I imagine surveying to occur, if one vector is longer than the other by 108 meters, I would say that's an elevation change, even on their model, right?
Mm-hmm.
But I mean, Blue, let us know. Let us know if anybody else spotted that as one of Blue's mistakes.
More or less what it should be? Let's find out.
Oh.
Here's an Earth radius by latitude calculator. At the south end, the Earth radius should be 6,372,822 meters. On the north end, it should be 6,372,713 meters. That's a difference of 109 meters.
As expected.
So now I want to show you some work that Walter Bislin did. Walter took Jesse's GPS data, the raw XYZ.
This is why Stingray was saying Walter was the man. This is modelling. I mean, it's a couple of years old. This now. I mean, maybe 2, 3 years old. So I mean, look at the graphics.
Wait till you hear what he says.
He's got Chikey's eye level in there.
Yeah. It says Chikey's eye level. Look at that. I'm taking it that's from up in the hotel room where
15th floor. Yeah.
Where they Soundly and his boys had a hotel party. Soundly, Jesse. I don't know who else.
Z data and generated a CAD drawing of the causeway. Watch what happens when we superimpose a picture of the causeway. That's a pretty remarkable fit, isn't it?
Yeah, it's definitely not likely backwards engineered or anything like that through CAD.
No,
You guys notice that? The data matches the visual.
Absolutely, to the
This is very, very crucial.
Yeah. It's really close.
You know it's bull, right? Because we know it's visual.
Better than that.
Doesn't get better than that. Yeah, you're right, Blue. Doesn't.
We can do one other interesting thing too, and this was always amusing to me. When flat earthers like Quantum Idiot decided that Google Earth was...
How many times does Blue want to talk about these people? It's like he's obsessed with them.
Was actually a
Always
flat model.
Attacking other people,
I couldn't
innit?
do anything except laugh. I know
We're all going to learn a new word now.
And you've probably drawn lines on Google Earth with the measure tool. But there's a feature in
Hang
there
on,
that you may
Bev,
not
can
be
you back
aware
that up
of.
a second to where he overlays the digital image over the photograph?
There. That's like the meld of the two of them.
Yeah, I'm just looking to see where that tower is that he's got there. That transmission tower.
That one. Yeah, and this one here.
Are they on the far shore or are they actually on the bridge?
Don't know. That's got to be on the far shore, that,
On the
hasn't it?
far
I
shore?
don't know. You'll have to ask Rakia. They may have one in the middle of the bridge somewhere.
Yeah, they may do.
I don't know where the... what is that, the water tower there in the background? Just about?
Yeah, you can just see the water tower there. They haven't modelled the water tower.
I'd say these are on the bridge.
The transmission tower?
Yeah, because he has modelled everything on the bridge, hasn't he? You know, like he's modelled the bridge, so that's why they'll be done.
No, there are no transmission towers on the bridge. You look at the picture.
See this down here? It's highlighted in yellow. It says refraction K 0.250 brackets medium. Temp gradient DTEC or something equals 0.00665 something layer inversion. So he's in his model and a globe model prediction with a load of factors of other things involved in it, right? It's not just a data like Blue said. Oh, it doesn't seem to be. I mean, I don't know why he's wrote that refraction thing on the model. Blue said it matches it. Isn't that weird? It might match it with all of this refraction details that they've got down at the bottom in order to make it match, perhaps. I mean, I'm just guessing. I don't know. You all right with that? Listen.
We can do one other interesting thing too, and this was always amusing to me. When flat earthers like Quantum Idiot decided that Google Earth was actually a flat model, I couldn't do anything except laugh.
Wow.
I know a lot of you have used Google Earth, and you've probably drawn lines on Google Earth with the measure tool. But there's a feature in there that you may not be aware of. When Google Earth comes up, it comes up with the line you're drawing clamped to the surface of the Earth.
What?
But there are alternatives. You can set it so that the line is not clamped to the Earth. It is a reference to absolute altitude, or
unclamped. Let me hear that back again.
Measure tool. But there's a feature in there that you may not be aware of. When Google Earth comes up, it comes up with the line you're drawing clamped to the surface of the Earth.
Anyone ever heard of that before? Google Earth clamps your line to the floor.
Nope.
A clamped line. No, they're not on the bridge. Oh, it's Blue talking. Oh, I see. I haven't heard Sim Blue. Hey, Blue. Good that you can come to watch. Clamped has anyone seen the clamped line Google option? Does he show us? I hope he does.
Yeah. He shows us. Yes.
Nice.
Unclamped.
Yeah, okay. Well, let's go back. I don't want to interrupt this. I know Blue will get upset.
And you've probably drawn lines on Google Earth with the measure tool. But there's a feature in there that you may not be aware of. When Google Earth comes up, it comes up with the line you're drawing clamped to the surface of the Earth. But there are alternatives. You can set it so that the line is not clamped to the Earth. It is a reference to absolute altitude, or absolute elevation if you choose. So this is what we would see in Google Earth. We would see the geoid. Now we've got a chord line, which we've been talking about, which would be a line from the north point to the south point of that bridge. But if we set the elevation just right above that chord line, we can generate a tangent line.
Ooh. At least it's an external tangent. Equipotential angle. Yeah. At least we got it right there.
But then it goes, if we set the elevation just right, what?
Yeah, I don't know what that. How do you set the elevation just right? I mean, surely law of identity states the elevation is what the elevation is. You can't set it. Seems a bit silly. Again, is this another feature?
Yeah. He shows it. He shows it in the software.
Okay.
Point to the south point of that bridge. But if we set the elevation just right above that chord line, we can generate a tangent line. And that way we can see the drop from horizontal. Let me show you a brief clip of me demonstrating that. I wanted to have a look at this thing in Google Earth. This is Lake Pontchartrain. You see it here. This is the north shoreline. That's the south end. I've drawn a line right down the center line of the south lane, the southbound side of the causeway. But it's not just a regular line. I'm using a Google feature that some people don't even know about. If I go to altitude, when Google comes up, it comes up clamped to the ground. Your line will be clamped to the surface of the Earth. I'm not using that. I'm using absolute. And I've got the altitude of the line set at 24 meters. I've also checked the little box that said extend the line down to the ground. Let's see what that's going to do for us. Let's go here somewhere around the middle of the causeway. I'd say it's right about in there somewhere. Then we'll just start zooming in at that point. And now you see the southbound lane and the line's running down the middle of it. And now I'm going to tilt it just a little bit so that we can see that in fact, the line is right at the surface, isn't it? Yep. Right at the surface. Very nice. Just as it should be, correct?
What?
Okay, let's see what it looks like on the end. Let's go down here to this end first. And let's tilt it a little bit. And uh-oh. Uh-oh. What happened? It's not at the surface anymore, is it?
Whoa.
Goodness.
Is that horizontal then?
Scoot along.
That there line is unclamped.
Sure we can
Unclamped. Is that an unclamped horizontal?
And we see
Yeah.
the line getting closer
Wow.
and closer. And closer to the surface. Till it's right on the surface. Right in there somewhere. And then as we continue...
Whoa, what's happened
down
to
the
those
south
lines
end
there?
of the
What
bridge.
happened there?
Those past there in the background, yeah?
Yeah. Let's just go back.
Yeah.
I mean, did you see it?
Yeah.
He's scooting along. See these lines here?
Just very nice. Just as it should be, correct? Okay.
Right,
let's
so
see what it
these
looks
grid
like on the
lines.
end. Let's go down here to this end first.
Right, look at the grid lines. Remember the
And
grid
let's
lines.
tilt it a little bit, and uh-oh. Uh-oh.
Oh, look,
What happened?
what's happened to them?
It's not at the surface anymore, is it?
What's happened to grid lines?
Goodness.
Distance.
See if we can just
Look at these.
Oh,
scoot
that
along.
is
What? They're
extreme.
still here. Look at it.
Wow,
Sure.
look,
What's
it's
going
almost
on here?
stationary there in the back.
And we see the line getting closer and closer. And
What's
closer
going
to
on
the
there?
surface,
Computer graphics. He's unclamped it.
till it's right
It's
on
gone
the surface.
wild.
Yeah.
Oh, look
think the
at
grid
this. Look
lines
at this
get
line here.
unclamped.
Look, watch this line. I don't know where it's a straight line, but look at this in the distance. Unclamping's done something, and then this
Wow,
rogue,
my God, yeah.
rogue white line here. Watch.
And then as we continue,
Whoa.
Look at the lines in the background.
Yeah. Look.
Yeah.
This one. This is one of them. Whoop. What happens
Oops.
there? Like whoop. Are you sure that's? Unclamping might have made it not. They're lat long. Oh, those are lat long lines, obviously. Fucking hell. Look at me, look at them. They're obviously lat long lines, bro. Unclamped. That's what lat long lines look when you've unclamped it. You've unclamped the system. Look at it. Whoop.
down to the south
It's
end
over
of the
there.
bridge.
They're not moving, those lines. You notice they're not moving?
Oh, they are.
Than I thought.
They are. We just
They
went
are?
past one of them. Yeah, we just went past one of them. It's
There
there
we go.
going.
Line started
Here's
to
another
climb
one.
again.
Is it? No.
A little bit more, and there we go. That end.
Look. Yeah.
Same thing. It's like the Earth is curved, isn't it?
No.
You could try this yourself. Well, I guess that's pretty much it. I hope this brief analysis helps
Copyrighted
everyone
this. I don't
understand
know. I
how
believe it's
that
copyrighted.
GPS raw data
Let's watch out.
can show us the shape of the planet that we live on. A huge shout out again to Soundly and Jesse and Walter for the outstanding work those guys did. It was truly a remarkable effort. And after seeing this, I wonder how the flat earthers are going to go about trying to deny it. Oh, I know.
Don't worry about the flat earthers.
That's how they'll do it. Hey, thanks for watching.
Thanks for watching. Oh, I'm going to get that.
Yeah, the line is right at the surface, isn't it?
Look at that.
Yep.
Unclamped.
Right at the surface.
See, they're here.
Very nice. Just as it should be, correct?
Are they that long or?
Okay, let's see what it looks like on the end.
No, they're northerns and easterns, aren't they?
Let's go down here to this end first.
They're your northerns and easterns. I take it.
And let's
And the
tilt
blue
it a
says
little.
that these ones in the distance over here are lat and long.
What happened?
So you can
It's
look,
not
see
at
the
the
way it's
surface
coming off
anymore,
and
is it?
it's curving over there and curving over there.
Goodness. See if we can just
See, what's
spin
this here,
along.
Essie? You see that one? It doesn't look like it's
Sure
moving,
we can do.
but that one comes past
Yeah.
See the line getting
eventually
closer
halfway.
and closer and closer to the surface.
The ones in the back, they didn't appear that they were moving.
Right on
No,
the
but this
surface.
one here is coming along, isn't it? He
Right on
crosses
the
over. Here it is. Whoop,
That big one, yeah,
As
yeah.
we continue
whoop, and there it is. See, it's gone.
down to the south end of the bridge,
Perhaps you should have gone that way on the.
you have to go further than I thought.
I mean, this Google's massively.
Here we go.
It's brilliant. I'm not surprised he couldn't. Jesse could have done this. You know.
A little bit more.
I don't know why
Yeah.
Jesse didn't go do this from the start. I mean, he could have
It's
just.
like the Earth is curved, isn't it?
What he could have done is just put a ruler on there, measured it, and gone, there you go, look. 28.5 meters. Here. Must be. Right, so, thanks, Blue. If everybody, hope everybody's been cleared up for that. With Blue. It showed conclusive proof of Earth curvature. Unclamping Google. And the numbers that Jesse has. One end of the bridge. The vector being 108 meters off the other one.
Well, we
no.
all learned about unclamping.
Yeah,
Sure, nobody heard of that. Thanks, Blue.
I don't think I'll bother making a video. I was gonna, if you'd have done something a bit better, Blue, I might be able to make some clips out of it or something, but there's nothing really new there. Apart from I like the tangent thing. Now, did Blue say that was horizontal? The unclamped line?
I'm not sure if he said horizontal.
No, but
I didn't even mention it.
It's got to be straight, hasn't it? Was that straight? Rather than putting a chord like Jesse did, is that Blue's unclamped tangent a straight line, or was it clamped as a tangent?
He probably meant a straight line because to them horizontal is a curve. So that line looked pretty straight to me, right?
Well, I think he said it was a straight line to start off with, and then he unclamped it. And did he unclamp it and make it a straight line?
I think the unclamping made it straight.
So when you drew it on Google, it wasn't straight. I mean, they were straight line distances, I'm sure.
I think. Yeah, I think that's how he envisions it. Like Google has the curve, the hump, whatever built in, and then you unclamp it. I think that's what he means.
Well, I thought whenever you did a line from A to B on Google, it was a straight line. Now, I'm presuming that is the same straight line distance, but unclamping it, like, puts it as a tangent somewhere or something, but keeps the same length, I'm guessing. And I'm guessing that one distance is actually a straight line, and the other distance might just put the Imagihump there for you. Might help you out with the Imagihump in case you're struggling. Unclamping might help you Imagihump.
Yeah, for sure. He plotted in the 24-meter hump in the unclamping tool.
Well, yeah, the hump is there because you see at either end it's lower. So in the middle, right, the middle part, you see it touching that line, but either end it drops. So that's the hump in the middle, yeah.
Yeah, okay. I'm guessing 20. Yeah, he put 20. Yeah, I don't know.
Correct me if I'm wrong, Blue.
It's all right. I mean, this will be a big thing. I mean, obviously, they don't want to teach us anything at all. So maybe they might not address them because we have questions. But hopefully, there might be some globers out there that have questions. I mean, maybe flat earthers might have some questions about it as well. I mean, who knows? I've definitely got questions. And I would love to hear from Jesse or Soundly. I mean, I didn't realize that Soundly was so involved with the GPS measuring of the presupposed curvature of the Earth. I mean, I still don't know where the curve comes from. I'm still unaware of the XYZ, how the XYZ, I thought Z was elevation. It appears I'm wrong, so the XYZ must be on a tilt somehow, and I'm guessing that the 108 meters somewhere is something to do with the tilt of one of the axes. I don't know.
Could I just mention something about the longest bridge claim?
Oh yeah, of course you can.
Yeah, it's actually quite interesting looking into it. Technically it is, but it was surpassed by a bridge in China and then one in Hong Kong. And the world record used to be done on aggregate, but they had to change it. So Pontchartrain is technically the longest bridge over water continuous, while there are longer bridges over water aggregate.
Yeah.
It's all technical stuff. Doesn't really mean much.
I don't know what his unclamping did as well. I'm just looking here in the bottom right hand corner, and it says elevation is minus 11 feet. I'm not too sure whereabouts that is. That's minus 11 feet. Might be just where his cursor is at the minute.
Yes, it sounds like a reversed curvature switch, in a sense.
Unclamping. I'm gonna look into it, but I mean, I can't see the use of unclamping.
They bend the horizontal when they unclamp it, and it turns back into the horizontal it should be.
You reckon the horizontal? Which one's the horizontal?
I don't know.
Where's the shortest distance from A to B measured on the map? I'm sure that I always thought that was horizontal.
Yeah, and if you do an elevation, if you go to the elevation on that, you'll see it across the screen linear, left to right.
Yeah.
Oh yeah, I don't know what the unclamping is, to be honest.
Unclamped Imagihump. Jose, it's level. You've got a really bad misunderstanding of level. But I mean, it's okay. A lot of people do.
Let's not forget it.
Yeah. The water is the level. Right. Okay, well, thanks for watching, everyone. Anybody got any other final points?
And then somebody says who?
Okay, well, it's UFC night, so we've got to go and get ready for UFC night. So
he unclamps the Google Earth line.
The Google Earth line.
That's what it says on the thing.
Nice.
So what he probably means the Earth.
Yeah, I don't know.
The surface of the Earth, the elevation.
But
yeah.
It seems Blue's put out another very short video of.
Oh, right, okay. Is he upset again? Like, I'm glad he's got some content.
Yeah, it's only a minute 59.
Should we have a look at it? Should we
make a load of shit up about a hump? That's what's happened.
But sorry, slightly butt hurt about something. I've just clicked off it, so I don't know where Blue Marble thing is.
Here's the thing in his own words. Google Earth line, unclamped and showing drop from a tangent.
Is that one of the new updates or something, or has it always been there?
It's in the chat, Bev.
Can't believe you guys have never heard of unclamping.
No, I know.
How long have they been using unclamping?
Wow,
Forever.
Blue, come on.
Doing any surveying. Don't bother surveying anymore. Just go on Google Earth and work out your drop.
Right, you want
Yeah,
to...
on site,
you
isn't it?
got the screen on there, yeah. You want to see?
Oh, go ahead, yeah.
This is blue marble. Not that he's triggered or anything, but...
What is this? Like a... something?
Hey, is that Gladys?
Oh, he's took his copyright off.
That's Gladys. I know
Yeah.
that sound.
Converging lines. So you would assume that at some point they meet at a single point, which would probably be the North Pole, right?
Is that the latitude and longitude?
Yes.
Time and an angle.
No, just angles. That's what latitude and longitude.
It's time. One of them's time, right? Longitude.
Oh no, it's two angles.
Mm-hmm.
I mean, you surely know what latitude and longitude coordinates are consisting.
Yeah, one of them's an angle to a light in the sky, and the other one
I think
is
you're confusing
time.
this. You're confusing this with celestial navigation, aren't you?
No, you've got latitude and longitude, two-dimensional coordinate system. One of them is an angle
Yeah,
to
yeah.
a light in the sky, and the other one is
No,
time.
no, that's not.
That's all, folks.
Okay, Blue, game on. I'll do the tangent elevation above the tangent plane video. That'll be coming soon. I'll not bother doing the Daffy Duck. But I mean, yeah. Anybody want to know about that? Look into it. Longitude. Latitude. Anytime, Blue, you want to come and have a conversation about this stuff? Come and have a chat. It's no good hiding away, being all like butthurt and making videos about stuff, unless you need content. Be good fun, and it's nice to see that we've got a nice crowd in.
I'm glad to see that Blue decided against falsely claiming copyright on his
Yeah, I know
logo.
it disappeared at the end, didn't it, on his
Yeah,
new video?
yeah. He heeded the warning.
Yeah. That was well worth taking the warning there from Hoymar, Blue.
Yeah.
Yep. DP said
thanks
that'd
for
be a
pass-
bad move. That.
Yeah. It's not wise to falsely claim copyright on logos.
Yeah.
Some serious repercussions.
Right, so Will, like I say, it's UFC night. Go on, DP, you got to be quick.
I was just going to say that, if you have original design logos that are copywritten, then that's fine. But if you plagiarize other people's work and use open source text fonts, you can't claim copyright on that. And I'm glad Blue saw the error of his ways.
Yeah. Different time zones, aren't they, in the longitude? I mean, I wonder why that is.
Yeah, I
that's
wonder why
really
you need
weird,
a clock and a sextant.
Oh, yeah.
Yeah, why would that be?
Never mind. There'll be a lot of training videos for Globers to come out how to unclamp your Google lines.
So you can get your 57 degrees at 4:30. That's why, isn't it?
Yeah. Yeah, so the link's in the chat. Anybody wants to come, we are in Discord. Well, it's UFC night, so special night. We'll probably be back tomorrow, obviously. Obviously, because there's going to be a load of butt-hurt Globers. And they're upset at Flat Earthers. They're like, please, guys, don't get upset at Flat Earthers. Don't get upset at Flat Earthers. Don't get upset at Globers. It's just models. We just deal in reality, and we're just after knowing it. So anybody, Blue, I like your idea. Could you please explain it to us a bit more? Because I'm still wondering, why is it a 28.5 meter hump? Because it's not noticeable. I don't know. Maybe bring some physics into it as well. See if we can work out that. Like real life physics.
And like an extra bit of addressing going over the 108 meter difference in the, what's it called?
The length of the vector from north and south vector arms.
Yes.
Yeah.
Mm-hmm. Yeah, that'd be nice to.
108 meter difference in a vector arm, and whether that is elevation or
taken
not.
from the center of something.
Yeah, supposed. Yeah. I think so.
Yeah. Pretty accurate then. It's from the center, the dead center.
It seems it. It must be.
It'd have to be in the dead center. Otherwise.
Yeah, I did hear about a wandering thing as well. But I mean, who knows? They get
a wandering center.
Much more. Yeah, they're much more accurate now than they ever have been. Okay, I'm going to call it off, and I'm going to put a Buster song on, though, for the end.
Yeah, nice.
Yeah, greatest speech. Thanks for watching. We'll probably be back tomorrow. I don't know. Well, let's see.
Check this back.
You have the love of humanity in your hearts. You don't hate, only the unloved hate. To those who can hear me, I say, do not despair. The misery that is now upon us is but the passing of greed. The bitterness of men who fear the way of human progress. The hate of men will pass, and dictators die. And the power they took from the people will return to the people. And so long as men die, liberty will never perish. Let us fight to free the world. Let us all unite. Don't give yourselves to these unnatural men with machine minds and machine hearts. Let us fight to free the world. Soldiers, don't give yourselves to brutes. Men who despise you, enslave you, who regiment your lives, tell you what to do, what to think, or what to feel, who drill you, diet you, treat you like cattle, use you as cannon fodder. Don't give yourselves to these unnatural men with machine minds and machine hearts. You are not machines, you are not cattle, you are men. You are men. Let us fight to free the world. You have the love of humanity in your hearts. You don't hate, only the unloved hate. The unloved and the unnatural. Soldiers, don't fight for slavery, fight for liberty. In the 17th chapter of St. Luke it is written, the kingdom of God is within man, not one man nor a group of men, but in all men, in you. You, the people, have the power to create machines, the power to create happiness. You, the people, have the power to make this life free and beautiful, to make this life a wonderful adventure. Then in the name of democracy, let us use that power. Let us all unite. Let us fight for a new world. A decent world that will give men a chance to work, that will give youth a future and old age a security. By the promise of these things, brutes have risen to power, but they lie. They do not fulfill that promise. They never will. Dictators free themselves, but they enslave the people. Now let us fight to fulfill that promise. Let us fight to free the world. Let us fight to free the world. Let us fight for a world of reason. A world where science and progress will lead to all men's happiness. Soldiers, in the name of democracy, let us all unite. Let us fight to free the world. Let us all unite. Let us fight for a new world. You, the people, have the power. Let us all unite. Let us fight for a new world. In the 17th chapter of St. Luke it is written, the kingdom of God is within man, not one man nor a group of men, but in all men, in you. You, the people, have the power. You, the people, have the power to make this life free and beautiful, to make this life a wonderful adventure. By the promise of these things, brutes have risen to power, but they lie. They do not fulfill that promise. They never will. Let us fight to fulfill that promise. Let us fight to free the world. Let us fight to free the world. Let us fight for a world of reason. A world where science and progress will lead to all men's happiness.